I'll say that the assignment for today is on uh, Delta Math, complex numbers. We're only going to get to organizing them and then adding, subtracting, and multiplying, and they work very much just like when we're doing that with polynomial expressions where you're matching like terms. The only difference is, let's hope this is going to work now for us. Those two most important things that we talked about last week, which were that, it worked. I squared equals -1, and that the square root of -1 equals I, right? You remember that? I was like, these are the two most important things you will learn today. And that is carrying on into what we are learning today as well, right? But to get started, I need to talk to you about how numbers are organized. When we first are introduced to numbers in the world of our whole life, we start by counting, right? And what do we start counting with? Like, if I'm like, count your fingers, what do you start with? It's not a trick question at all. Exactly. We start with one. Our counting numbers are like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. And they're infinite, right? They can go on forever and ever because we can always just add one more. Like, what's the last number? Well, infinity. What's infinity? I don't know. We just keep adding one to the end of whatever the next number is, right? And we call those the natural numbers. And for the longest time, those were the only numbers we had, right? Were the natural numbers, which is, right, starts at 1. Right? 1 to forever. Let me do it in notation, right? They go from 1 to infinity, right? And for a while, that was like as big as it got. That was the whole world as we knew it, started with the natural numbers, right? Now, if I'm counting and I have, say, 1, 2, 3, 4, 5 things, right? And I say they're apples, and Jacob eats 3 apples, and Valerie steals 2 apples. How many apples do I have left, right? Jacob eats 3. Valerie steals 2 because she doesn't want Jacob to eat all of the apples. How many apples do I have left at the end of this? 0, right? None. But here's the thing, back in the day, 0 didn't exist yet. We had to come up with something to call it, and we called it 0, but it equaled none. And so that changed the number system for us, right? We had what was called the whole numbers after that, which was the set of natural numbers. It was all those natural numbers, which is infinity, right? It goes on forever and ever. It never ends. It's humongous. It's bigger than we could ever get to because there is no end ever. It's infinite, right? But then we added 0, right? Which was the whole numbers. And it went from 0 all the way to infinity. So it had that set of natural numbers, right? It included that whole infinity of natural numbers. But now we had another infinity that we called the whole numbers, which was one more than the other infinity, right? Because it started, but really not, because they're both infinite. They both go on forever. So they're both like technically the same size, right? Because they're forever. It's just one starts earlier than the other one, right? And it contains the other one inside it. Does that make some sense? I hope so, because I love talking about this stuff. I love talking about numbers in this way. I didn't lose 20 bucks. So first we got no apples. So I go, you know what? Valerie stole those apples and Jacob ate all of the other apples, but Sergio wanted some apples. So I'm going to be like, you know what, Sergio? When I get some more apples, they're yours, right? So say you want like 3 apples. I need 3 more apples, right? I am now down 3 apples because I need to give Sergio 3 more, right? So if I started here at 5 apples, right? And then Jacob ate 1, 2, 3, 4. I need to make these bigger. We'll call this 0. 1, 2, 3, 4, 5. This is 0 apples, right? So Jacob ate 3. 1, 2, 3. And then Valerie stole 2 and I'm at 2. Well, Sergio, I'm going to owe him 2 apples. So where am I in the apple count now? Valerie's right? I'm at -2. And so we had to start talking in terms of negative numbers, right? And it kind of moved us into debt, right? And so we had these, what we call the integers. Now we call them Z. Z is the letter we use for integers, and I will get into the Y at Z, not Y, it's Z, at some point. But basically they run whole numbers, right? From negative infinity all the way to positive infinity, but they're like -2, -1, right? They're whole numbers still. They're not fractions or decimals. They're whole numbers. They just move us into the negative side, right? They're still counting numbers. Now we're just counting into the negative side, right? And they're both infinite. They're infinite in every direction, right? This one, infinite in one direction, right? The natural numbers, they start at 1, they go for infinity, right? Now we got the whole numbers. They start at 0, they go for infinity. Now we've got these integers. Well, they're still the counting numbers. They still go for infinity, but now they go for infinity in the positive direction and the negative direction. And I don't know if you guys have ever seen or read the book, The Fault in Our Stars. It's a real tearjerker that will make you sob. But they talk about how some infinities are bigger than other infinities, which is kind of a misnomer, but kind of true. In mathematics, as we move on, we talk about countable infinities, something being countably infinite. Yes, John Green did write that book. And my oldest daughter just read it again last week, which is what made me think of it, because she was ugly crying in the living room the other day. So, which is what it did to me when I read it too, but it's really beautifully written. Yes, some infinities are bigger than other infinities, but no, they're technically not. Right? Because the infinity of whole numbers is bigger than the infinity of natural numbers by 1, right? But really it's not, because they still both go on forever. They just start in different places, right? We could say the same thing about integers. We could say, well, this infinity is bigger than whole numbers and natural numbers, because whole numbers and natural numbers are enveloped inside there, right? They're a part of that group that is integers that goes from negative to positive. But technically they're still not, because they can still both go on forever and ever and ever. It's just one can go on forever and ever and ever in 2 different directions, right? One towards the negative and one towards the positive. Such is life, right? You can go to the negative. We could put a lot of lessons into this. And then next we get into the craziest part of infinity, which is Q, which we call the rational numbers, which is funny because things that are happening with that letter I don't consider all that rational anymore. I'm not going to put in that it's the rational. I'm just going to shoot. And that was shoot. I did not swear. Just in case anyone was wondering. Now, the rational numbers also go from negative infinity all the way to infinity, but they include all the fractions, right? So they're whole numbers, right? And fractions, or I should say integers and fractions. That's probably a better way to look at it, right? And so all of that is contained in here. And what that says, this is kind of the cool part, right? When we're talking about integers, checking the time to make sure I have actual time for the assignment. When we're talking about fractions, there is an infinity in everything, right? If I have a number line, right, and I'm looking at it and I have 0 here and 1 here, there is an infinite amount of numbers between that. When we bring it into fractions, we can get infinitely smaller, right? There's no fraction that ends. It can keep getting smaller. If you think about this, if I have 1/2 of that, that is a point in the middle, right? And then if I have 1/2 of that, I can always have half, right? Like then I have 1/4 or 1/8 or 1/16 or 1/32. And I can always make that space smaller and smaller and smaller. And I can do this for infinity, right? So there is an infinity between 0 and 1. Is it bigger than the other things that are infinite, right? That's just between 0 and 1 in something that goes all the way from negative infinity all the way to positive infinity. I know it sounds terrifying for some reason, and I get that. I do actually totally get that, right? And this is just like a grain of sand in what there is to know about mathematics. Now, all this stuff we've talked about falls under the category of real numbers. And we thought for the longest time that everything revolved around the real number system, right? This is our real numbers. In here, we also have the irrational numbers, which are like pi and the square root of 2 and things like that that can't be written in the form of a fraction, right? So this is the real number system right here. We thought that mathematics revolved all around that because that was all we knew back in the day. But really, it's just like when we thought that the sun revolved around the earth instead of the earth revolving around the sun. But what really happened is that the real numbers were actually part of a bigger system of numbers, which are, let me get rid of this right here so that I have room to draw it. Are this box right here that's going to go all the way around it, right? They are part of a system called the complex number system, right? And we make it with a C like that, equals complex. And the complex number system has what we call A plus BI. We have these numbers that have real numbers, real parts, and then they also have imaginary parts, right? And that is what basically the complex number system is. And then it gets even crazier, but we're not even going to get into that ever in this class. Down here, we have like I, which is the pure imaginary numbers, or we called it BI because they could have an imaginary number, a real number multiplied to it. But this is what we were talking about earlier, right? the last time I saw you, we were talking about the beginning of imaginary numbers, and now we're moving into more of the complex number system. They work a lot like dealing with any variable that we've used before. The only thing we need to know that's different when dealing with them differently than a variable is that I squared equals -1 and that I equals the square root of -1, right? And if we come into anything in that variety, we have to go through and replace an I squared with a -1. Ultimately, it just usually changes the sign of whatever is in front of it. And so what we're talking about today is A plus BI, right? Where we have something that is real plus something that is imaginary. When you are dealing with complex numbers, they are always written in this form. The real number comes first, then the imaginary, right? When we have them, when we're factoring them, they always come as complex conjugates. There's no way I'm getting to that part of this today because I only have a few minutes. But all of that talking that I just did was to get you to the point where we understand what these are, right? And today we're just talking about adding, subtracting, and multiplying them. So when we are adding complex numbers, if I have -11 plus 3i plus 9 plus 2i, when I look at this, it's just like when we're talking about a variable. If we're adding two binomial variables together, if this is addition, right, the parentheses don't matter. We could just rewrite this as -11 plus 3i plus 9 plus 2i, right? And then we're going to combine our like terms, remembering that we have to have the real numbers first. So we're going to go with -11 plus 9. Well, that's -2. And then we'll go 3i plus 2i. Well, that's just plus 5i. That's as far as that can go at this point, right? I can't really take that any further. But it combines just like before, right? We've done this before, right? Think of it like an x. The only time it doesn't behave like a variable, like it's x or y, is if we have an I squared or a square root, right, of -1. So if I'm subtracting, this is where you guys will mess up. And you'll be like, I'm doing this right. How come it keeps telling me I'm wrong? It'll be because you're wrong. Do you like that? I like that. That was my best line right there. I was really proud of it. If I have, say, 7i minus 2i minus 2 plus 6i, this subtraction doesn't matter so much. It's this one right here that matters. Because before, when we were adding right here, we could just take everything out of the parentheses, right? But just like when we're dealing with adding or subtracting polynomials, we can't do that when we have this subtraction on the outside, because what it's saying is -2, but it's also saying -6i. And so we need to write it as such. This will stay the same, right? This would be, oh, I don't know why I wrote this as 7i minus 2i. I just wanted this to be 7. Am I going to rewrite it? Yeah, because it's going to mess everything up if I don't. I apologize for that. So here I have 7 minus 2i. This becomes -2 minus 6i, right? And now we can combine the like terms. So I'm going to do real first, my real part first. 7 minus 2, well, that's just 5. Minus 2i minus 6i is minus 8i. I. So that did not change things much, right? It's just remembering that when I do that subtraction, I have to distribute it through to each piece. Will you mess it up? Absolutely. And you'll wonder why you're wrong. And then you'll go back and watch this video that's way too long for what it needed to be, but whatevs. I'm not the one watching it. What if I have something crazy like, ooh, I only have 10 minutes left. So I'm going to go, instead of going into something crazy, I might make an additional video with a bunch of sample problems. And I'm going to take you just into multiplying complex numbers. Because this is where things change for us. Everything else is just like when we're adding or subtracting anything with a variable, right? The only difference is we write the real portion first, right? We have to write it in that term. Here you really need to remember that I squared equals -1. So if I have, for example, say 2i times 8 minus 3i, the quantity 8 minus 3i. When I'm multiplying this, I have to distribute, right? This becomes 2i times 8, which is 16i. And this becomes 2i times -3i, which is -6i squared, right? What is I squared? I'm looking in the chat box. I should see everybody typing this into the chat box. But instead, I only see Sergio, who I should like buy lunch one day for answering all my questions. I right? -1. So ultimately, what that does is that changes this to 16i minus 6 times -1. So 16i minus 6 times -1 just gives me plus 6. Sorry, 16i. Don't mess that up. Now, can I leave it like this? No, because I have to switch the order of those because I have to have my real component first. So I wind up with 6 plus 16i, right? Will they all be that simple? Heck no, right? I would never let that happen. But they don't get significantly harder either. What if I have, I know I changed up the color finally, right? That's what you're thinking. I don't know why I keep doing that. I meant to erase, but I forgot to flip the pen over there. 7 plus I times 4 minus I. Here we'd have to do the old distribution, right? FOIL, if you guys remember FOIL. I don't like to use FOIL because it only works if these are each binomials. But ultimately, what I'm going to do is I'm going to take the 7 and multiply it times each piece, right? 7 times 4 equals 28. 7 times -I equals -7i. Once I've played out the 7's been multiplied to everything. Now I'm going to move on to the I. I'm going to go I times 4. Well, that's plus 4i. Then I'm going to go I times -I. That comes -I squared. Right? And now we're just going to combine all of the stuff. Who knows what I'm talking about right now? Jeremiah, Valerie, we're having a weird conversation here. Huh? What am I saying? What am I saying? What do I have to do right now? What's the next step? I just said it. Just wanted to make sure you were listening. You guys are very, very chatty in there. You have to combine your like terms, but we have this I squared on the end. What is I squared? -1, right? So technically now I have 28. Well, I've got minus 7i plus 4i, so that's minus 3i minus negative 1. What's minus negative 1 times negative 1? Right, just changes the sign. So this becomes, ooh, what the heck, man? Plus 1. And so now when I combine my like terms, I wind up with 29 minus 3i. Real number first, imaginary part second. Why do I keep saying that? Because in your delta math, if you put it in wrong, you will be wrong. Right? You will be wrong, right? When I do this stuff, once I see this, like if I have negative I or negative 3i squared, like if I have negative I squared, negative 3i squared, I automatically just put it in as the opposite sign. So I would automatically, I wouldn't even write this as negative I squared. I'd write it as plus 1. If it was negative 3i squared, I would put it in as plus 3, right? But for the sake of showing you guys, I want you to see where that's coming from, right? 33. I got 4 minutes, man. I'm going to do it. Maybe I'm not. I'm going to make this afternoon today. I think I'm going to make a video with a bunch of sample problems on it for you guys, just so that you can kind of go through and see different kinds of problems done. I'm not getting into dividing or complex conjugates. That's what we're going to do for the latter part of this week. And so you'll have more, another assignment for that. I knew I wasn't going to get far today because I knew I was going to be getting really chatty in the beginning, which I don't know. I thought was kind of a fun conversation myself. Like I think that's all super interesting. I took a course in college called the History of Mathematics, and it's kind of as old as time. So it's really kind of a cool thing. I'm gonna turn off the video.